All right, so we're gonna pick back up. I think we left off last week with the mobilization. I left y'all with that problem. I'm gonna try and work through that problem this time because it's probably gonna be on the test, which is coming up on next
weekend.
As a matter of fact, it is. It's a week after Sunday, right?
Correct.
The 25th.
Yeah.
So that test is coming soon. So we've discussed that immobilization is the transformation of inorganic, immobilization, inorganic to organic. Remember, I've struggled with this whole net immobilization, net mineralization, that the ideal microbial diet is a carbon to nitrogen ratio of about 24:1. So somewhere in between here, we're kind of in that like gray zone. It'd be really hard to determine the net immobilization or mineralization. It'd be very minuscule and probably would amount to a hill of beans. But once we get above 30:1, we're going to get immobilization, and we're going to look at that in class. And then if we get below 20:1, we would have a net mineralization, which is the transformation of organic back to inorganic. So there's this, y'all remember the equilibrium arrows from chemistry? So this reaction, this process can go both ways depending on the carbon-nitrogen ratio. And the reason for that is because those microbes are going to need that nitrogen source as energy. So they're really using just the nitrogen out of that, and the rest is kind of an oxidation and a reduction, whether it's going from an inorganic back to organic, where we have an amino acid or some protein. All right, so this is kind of the problem that we're looking at. This is kind of after where's the crop at? Does it say the crop? It doesn't. So this is going to be a crop with a high carbon nitrogen ratio of 60:1. Our yield was 3,000 pounds of residue. We know that 40% of that residue is carbon. So that's just a simple multiplication where we multiply the biomass times the percent carbon to determine the mass of the carbon. From this mass of carbon, the microbes need about 35% of that in order to live. Just like we need food, they are a carbon-based organism, therefore they need carbon in order to survive. So they're going to take 35% of this 1,200 pounds. And that is going to give us, and we'll look at this in step by step just to kind of go over it, but of the 1,200 pounds, 35% of that is used by the microbes. Therefore, 420 pounds, the microbes need 420 pounds of the carbon from the residues. This 8:1 is a kind of a standard number. This is the carbon to nitrogen ratio of the microorganism. Just like our bodies are 75-ish% water and 25% other material, or whatever that value is, same principle. So since we know that once we do this, we know that that the microbes are going to need 420 pounds of that, and therefore they would need 52.5 pounds of N. So 420, this is basically just if you did 420 divided by 52.5, it's 8. But if you put this together, that ratio is 8:1. So once we determine what the carbon is, then we can figure out how much the microbes need, because they need 8 parts of carbon for every 1 part of nitrogen, or 1 part nitrogen for every 8 parts carbon. So we know that the carbon nitrogen ratio, and this is going all the way back from this value right here, we know that the carbon nitrogen ratio of the residues is 1200 to, so it's 60 to 1. So there's 20 pounds of nitrogen in those residues. And then from there, it just becomes a simple subtraction. The microbes need 52.5, so this is the bill. You've only got $20 to pay the bill. We got to find $32.50 somewhere else. That's your fertilizer. All right, so let's go over this kind of step by step. Here's our information. Remember, we have 3,000 pounds at 40%. Our carbon nitrogen is 60 to 1, and the microbes need 35% of that. So step one, we're going to determine the C content of the residues. That's multiplying 3,000 times 0.4 with 1,200 pounds of carbon residue. So it really helps if you put what you're actually trying to find. Next, the microbes need 35% of the 1,200 pounds. I guess this is kind of be like a paycheck. When you think about it, here's the paycheck, here are the taxes, or I guess, here's the paycheck, they take out 40% of that in taxes, you're left with 1,200. Here becomes the bills are due. And then here's where we've got this 8 to 1 number from. It's always going to be 8 to 1, typically. It might be 7 to 1, it might be 9 to 1, depending on the microbes, but for this purposes, it's just 8 to 1. Doing the math again, this is a simple cross multi, this is an equality. Back to pre-algebra. Divide 420 by 8, and we get 52.5. Next, we're going to determine the N content of the residues. We know that the carbon nitrogen ratio is 60 to 1. We know that we had 1,200 pounds of residue that was available. So there are 20 pounds of nitrogen in those residues. Next, it just becomes a very simple equation. We just have to go about finding carbon residue, carbon microbe, N microbe, and N residue. How about trying to solve this one?
Can we work it out?
Yeah. We're gonna. Okay, so what's the first step?
Hang on one second.
Took all the good markers. I probably have them all in my office.
So first you multiply the pounds by the percentage.
So this is
4,575 pounds of residue. That's 52%. Equals 2,379 pounds of carbon in the residue.
so 2,379 pounds. This is C residue. All right, we'll put this up here. We got,
I think Jacob's downstairs.
tell him to come up here.
He just texted me and said, you should come to nitrosis class.
Tell him he should come to nitrosis class. C residue.
I'm in nitrosis class. You're on speakerphone. in Natchez' class. You're on speakerphone.
He doesn't know we were supposed to meet up
Where
here.
y'all at?
We're upstairs in 137.
That was my fault.
What room is it?
137, Plant Science Lab.
Oh, okay.
Okay,
Alright, in a second.
okay. Bye.
Alright, so our C residue is 23. I don't think that's right.
Like, you don't think that math's right?
It is. I didn't think that the C residue was right. C residue is 2,379 pounds. Next.
And then figure out the percentage that the microbes use.
Okay, so
So 2,379 pounds of C-res times, did we have that on the slide?
yeah, 35%.
Is it always gonna be? Like,
Now, I'll probably give you the number, but it's gonna be pretty close.
okay,
I'll give you the number just to trick you. Just to make it like not basic.
right,
Because like you don't know what that number is. Like it might be 35. It really all depends on the microorganisms.
okay,
But that's probably a typical ratio.
okay. 832.65 pounds
832.65.
of carbon
Pounds.
microbe. Is that right?
Yep. See micro. 832.
And then the ratio,
And then the ratio.
832.65 pounds C microbe over X pounds of EN. And it's an 8-to-1 ratio, right? 8 over
Yep.
1. No?
Yeah.
Yeah. So 104.08 pounds of N micro per acre. Is that the right way to write that?
It's just yeah, I think, yeah, it is because we did it on an acre. 104.
And then we try to find the N content,
Of the residue.
the residue.
And that was 37.
Okay, so you just set that up as like,
The same way we did here. This is now 37x.
was the 37 given?
Yes.
Okay.
Divide both sides by 37. And that equals. And then we have 4.08 pounds of N microbe minus 64.29 pounds in residue.
$39.79. There's a computer program called Doodly. Have you ever used it?
Do I want to?
It's pretty cool. Mom and I have it for
Yeah.
like Kimco stuff. But you'd be able to do like, you can do one line of problem and then like it writes out each line, but it's gradual. And you can voice over it.
Yeah,
But it's really user friendly.
yeah. That's like $67 a month though, isn't it?
Yeah.
I want to-
I think you can get it cheaper. You could probably get it cheaper because like you might get a university discount.
Right. But it's something that I would. I think those videos would be awesome.
Yeah.
All right. Any questions on this? This kind of makes sense? I made it pretty straightforward, just like this in the notes. Like it's step by step by step by step. All right. So this was for, let's do another one. I really wish I had a better marker, man. My markers suck. They're supposed to get me some good ones. Fennel asked for like the markers that I had for downstairs for my lab, but I have yet to see anyone move to getting those. All right, so here's the next problem. We have a hairy vetch cover crop that produces 3,000.
This calculated.
I have not watched any of the videos for the last 3 weeks.
It's in the nitrogen cycle. It's like the step.
Oh, yeah,
It's
yeah.
the step for immobilization, wherever that is. But it's just how much, like, how much nitrogen the microbes need.
I got you.
And so, like, by how much they need, you can figure out how much fertilizer with nitrogen you need to apply.
That sounds pretty straightforward.
He said he was sorry he didn't email out that we were up here. I was like, why did he text me that? He's not even here.
That's
Hairy vetch cover crop that produces 3,721 pounds of residue, 32% carbon. The carbon to nitrogen ratio is equal to 11:1. Again, the microbes need 35%.
about bothering you guys?
Nope.
You have a class, giving a test.
I don't know
It's
about
a
giving
test, it's the
test, but-
final,
This is the final?
final right now.
Good for you.
We're checking out early.
Good.
I wish.
I'm contemplating giving that out to my classes.
Do it.
Just to be done.
I know.
I'm here for it.
I know you are. Enough of this bullshit! Sorry, gang, but I just can't hold it back sometimes.
Whenever I'm seeing that mask, it makes me think of like a bandit. You see like robbing trains.
Yes.
With that bandana.
Alright, what's our first step here? Jacob, what's the first thing we need to do?
Damn, I'm still writing.
Go ahead, Madison, you do your thing.
I don't know.
Okay,
My internet's been weird. I haven't been able to get to the videos.
and first we need to find the carbon content of the residues.
One 1,190.72 pounds of sea res. Can I abbreviate like sea res and sea? Okay.
What was that number again, Jacob?
$1190.72.
Alright.
You know the next step?
Jacob will do it.
Okay.
We're 16.752.
So we took, I actually made this 1191, just to make the math easy, times 0.35, and that is equal to 417 pounds sea microbe.
Isn't it 3.2?
What?
Is it 1191 times?
Show is. Show is.
That was it. No,
Well,
I mean, I did
no, it
that.
wasn't.
It's 3.5?
It's 3.5. We're looking for the microbes now.
Okay.
Yeah, it's about that 35, yeah, that 35% micro.
The 35, yeah, this
Okay,
35 is,
okay.
this 35 is generally gonna be. Yeah, so it's kinda like this, and then times that, whatever's
Okay.
left over. So we had 417 pounds of carbon, so this is sea microbe. 417 pounds of sea. Let's see here. carbon to nitrogen ratio is equal to 11 to 1. So, nope, this is gonna be the 8 to 1. This is the 8 to 1 part.
Was the 8 to 1 a given, or?
Yes.
Okay.
So I have 417 pounds of pounds of carbon. We need to know how much nitrogen is in there, how much nitrogen the microbes are going to need in order. This is part of this increasing the biomass. So that ratio is 8 to 1. If we flip that equation around, it's algebra. 8x equals 417. We'll divide both sides by 8, and x equals, this looks like 52.15. Good, Jacob?
Yeah.
Alright, so I just made this math a little more simple. We have 1191 pounds of C residue. And we have X pounds of N residue. And that ratio is 11 to 1, or this looks like 11x equals 1191 pounds. I think maybe I got this too much up. This. 1191 pounds. C residue. X pounds. N residue. That's 11 or 11x equals 1191 pounds. It's supposed to be C residue. Divide both sides by 11, and X is equal to 108.3 pounds in residue. So, microbes needed 52.15. We have 108 56.30 pounds supplied by residue, which gives us
50, my math, I rounded different, 56.12 pounds of in excess. Wouldn't it be in excess?
it is, it's correct. So when we have this negative,
It's,
that's pretty close. I mean, my math over here is 56.15, but that's just rounded. That's just rounding error. You wouldn't have gotten that wrong if you had put that on the test. And just to follow with the formula that we were talking about immobilization potential. But we have a negative immobilization. And if it's not immobilized, then it is
mineralized.
mineralized, correct. So I kept it this way just to show you that we're talking about a negative amount immobilized. This is like excess. That's a very good term for it, which also means it's mineralized. So the carbon nitrogen content of your residue is really going to influence how much fertilizer you might need to apply next year. So we plant cover crop and we get a credit of about 56 pounds, depending on the cover crop. But I mean, this example was pretty close to real. So we would get 56 pounds of nitrogen that we don't need to apply. So that saves our fertilizer cost. And so ultimately you would go back and look at what it costs to plant cover crop. You're gonna get some benefits from that
Right.
over the course of the winter. And you're also gonna get this 56 pound credit. So kind of understanding this part of it, and it's really just about the carbon nitrogen ratio, and also the biomass. Those are the only two things that are really going to change in this equation.
Do we get to a point that too much excess is excess?
No,
No, okay.
no. So my boss at Mississippi State was doing this type of thing with cover crops.
Yeah.
And he was basically not putting nitrogen on and seeing how long it took before the yield difference between applying nitrogen and just using cover crops was not significantly different.
Okay.
To say that you can get 75 or 100, 125 bushels per acre without ever putting out any nitrogen,
Right.
that's a win.
Right.
It's not at I guess my thought process when I talk to these producers is, do you want to win at the elevator or do you want to win at the bank?
Right.
So if you don't have to pull any money out of the bank and you're still getting 125, your inputs are less, therefore you kind of win at the bank.
Right.
And then if not, you only have to put a little bit of fertilizer out, and you might not need to, you don't have to use so many tons of urea that's like $600 a ton right now.
Right.
So these are like the things, this is how you can determine like your in credit.
Okay.
Like a fertilizer management balance sheet. Like, this is how much we think we're gonna get and this is how much we're gonna end up needing to apply. That's how you get very efficient and effective with your resources. And then all that really comes down to is how much did the cover crop cost versus the 56 pounds per acre that it saved us in fertilizer.
Right.
And so if urea is $600 a ton, what's 600 divided by 2,000? It's gonna be like 30 cents.
Yeah. 30 cents.
Exactly.
0.3.
0.3 dollars per pound, and 0.3 dollars times 56.
16.8.
You save $16.08 on an acre. Whatever the cover crop, cost of cover crop.
Which probably isn't that much, right?
Probably not. Probably not. Plus all the benefits that you get, like there's a whole bunch of other intrinsic benefits from this.
Right.
But really all that matters is how much it hurts my pocketbook.
Right.
So you're saving $16.08 on an acre, and this number is likely to be more.
Mm-hmm.
That I just happen to make up a carbon nitrogen ratio and those residues. So the amount of residue, like the yield, is where you get the change. So more biomass, more nitrogen.
So how would you, like, is this how the question will be asked, or is there a chance that you're gonna give us the end result and we're gonna have to work backwards?
No, I wouldn't do that
Okay.
for you. There's no point. That doesn't make any sense.
Okay, I was just making sure.
Yeah, no.
Because
it
my
would-
brain has a hard time going backwards.
So does everyone else's.
Okay.
That's when you know you understand it.
Right, I don't understand it that well. Yeah,
Doing that backwards would be impossible.
okay,
I mean, it would be real difficult.
Okay.
Like, I have the capability, it's just not practical.
okay,
It doesn't, I mean, you got a 56-pound end credit and your carbon to nitrogen ratio is 11:1, find out what the original carbon,
okay, I was just making sure.
trying to get good evaluations here. Right? Like, there is no, some of my other math problems I do, but they're very simple. They're like, duh, you should be able to do reverse algebra. But this is something that's more complicated. But just to understand that there are 4 things you need to find.
Okay,
They're given in the problem. If you solve them in order, you'll come up with this number.
okay,
If it's negative, then it technically means it's mineralized.
my dog just peed all over the bed.
Your what?
My dog just peed all over the bed.
You have one of these? Maybe somewhere. I mean, it's the same one that we did.
Yeah, I've got the other.
They had to do the hard one in fertility.
My friend Rachel, she's like, you can get a dog, you can get a dog. And then I hear her go to their house, I hear horror stories.
A haircut might work.
I'm getting a haircut later today. Yeah.
Dog or haircut.
Yeah. She's like, you need to get a dog, you need to get a dog. And then my other friend will be over there, and they're like, well, my dog shit under the bed, and then the Roomba found it and spread all on the floor. And they're like, oh, well, our dog pees on the floor twice a day. I'm like, y'all are really not talking. They're like, you should still
You
get a
aren't
dog,
helping.
though.
Yeah, no.
I'm like, you're really not talking this up.
Nope, not at all.
Yeah, I'm getting a haircut for this class. It's getting a little ridiculous.
Man, wow, we made it through a whole bunch of stuff. All right, so finally, I guess in the last class I made it all the way through nitrate leaching and this clay fixation. So finally we have these 2 gaseous losses to the atmosphere. One hurts our pocketbook, one hurts the environment. So in fertility we go over the actual processes of how this ammonia volatilizes. It's really just that the soil is going to require one of these hydrogens in order to reach equilibrium, and therefore NH3 is a gas and it is given off into the atmosphere. About 30% of the nitrogen that you apply can be volatilized. So you go out and apply 100 pounds, you really only applied 70. So what do producers do? If you lose 30%,
You go up 30%.
you go up 30%. So what's 30% of 130?
City chickens don't know.
39.
39. So 130 minus 39 is 91. So you thought you put 130 pounds out, but you only put 91. So by adding more fertilizer, that is not the answer. You're still losing it. And it's because of the soil pH that as we become more alkaline, what happens to the hydroxyl concentration? As the soil becomes more acidic, what happens to the hydrogen concentration? It goes up. So as it goes alkaline, what happens to the hydroxyl concentration? It goes up, correct. The ability to hold on to that ammonium, our crop residues are going to create an environment where that process is exacerbated or sped up. And so this is our right source and our right rate. This is a look at that urea hydrolysis, and just to kind of make things simple, that urea, the granule that you spread with water, forms ammonium carbonate. We get 2 of those hydrogens from the soil, which makes the pH more alkaline. And then we have 2 ammoniums carbon dioxide that's given off as a gas, and water. Well, because we're always trying to be in equilibrium, is that not on there?
Looking for it. Yeah.
Should be near the end.
Yeah, yeah. Okay. Good.
So as the pH increases right here, we're going to get this equilibrium back, and one of these hydrogens will now try to form another water to balance that out. We have ammonium gas. Not that you would need to know how to write that on an exam, but just to understand that it's the pH that is causing this exchange of hydrogens that ultimately causes that volatilization. This is probably something that is more for your kind of reference and information to kind of look back and go, how come I applied this fertilizer and nothing happened? Depending on the source, you can get 30 to 50% of nitrogen loss, and so it's important to understand those things before you go applying fertilizers. And then we have the final step of this is denitrification. So this is going to complete the cycle where we went from fixation, immobilization and mineralization, ammonification, nitrification, leaching, plant uptake, 2-to-1 clay fixation, or denitrification. And this is going to get into gas back into the atmosphere, which is the whole goal. So what you'll notice here is that we are undergoing a reduction process. So we went from nitrate NO3 negative to NO2 negative to NO2. See how we're losing oxygens, we're gaining hydrogens or electrons, and then finally to N2 gas. So the microbes are using this oxygen as an energy source. Why would the microbes need oxygen?
To live.
Under what conditions would the microbes require this oxygen?
Anaerobic.
Anaerobic conditions, because there's no oxygen, right? So we had 9 inches of rain, we've got this nitrate that's in the soil, and all of a sudden you are drowning these microbes and they have to live, and they are taking the oxygen off of this nitrate and eventually converting it back to N2. Now, I guess I've been kind of trying to make sure about this N2O gas thing, but once it becomes nitrate and starts this process, it's also not available to the plant. So, you applied this fertilizer, you did everything you were supposed to do, 9 inches of rain comes, sap takes all the oxygen out, and now the microbes have done their job to the fullest and then converted this nitrogen back into atmospheric N2. So to help this out, we were going to need a high pH because our hydroxyl concentration is greater, and therefore we would be able to remove those oxygens easier. It makes it easier to reduce that molecule. So heavy rains, irrigation, snow melt under anaerobic conditions. Some of the ways that we can combat this is by using a urease inhibitor, which is stopping the conversion of urea to ammonium, or we can use a nitrification inhibitor, which is stopping the conversion of ammonium to nitrate. And if you get out there and you ever need it, don't worry. Just call up a rep. They'll help you out. And then finally, we're going to end here with organic sources. This is going to be like poultry litter or whatnot. Cow manure. There are 1 billion tons of waste generated. We are actually even using human waste as a fertilizer source. %75 human waste. So they have to get rid of our crap. Be here all semester. They have to get rid of our crap some way. And so they have done enough of the processing such that it is safe. There's a ton of research going on about this. And these biosolids are then processed for land application. just to look at some of the different types of manure that they're using. These are going to be in our lagoons and our CAFOs, whole nother class, whole nother thing. Some of these organic sources you might use in a nursery situation. I can typically remember them coming in like a little box, looks like a cereal box. But there's enough that you can sprinkle on a plant and you can get some of the benefits from having this organic matter.
Can we go back to that slide? In soil fertility, I remember there being questions on a test about, like, we were given like fruit pulp, bone meal, blood meal, and something else. And it was like, which one of the, I don't remember how the question was worded, but I remembered not getting it right. Do you know what I'm talking about?
I do.
What, can you explain that to me?
What?
Like what the question was and like how to, like,
I guess the question is which one has the lowest carbon to nitrogen ratio? Or which one would, is there a carbon to nitrogen? Yeah. So which one would result in immobilization or mineralization? So let's look at blood meals. Carbon to nitrogen ratio of about 3. Immobilization or mineralization? What's the ideal microbial diet need?
is that the 8 to 1? 11 to 1? 35 to 1.
30.
37 to 1.
At what carbon to nitrogen ratio do we get a net immobilization?
20 to 1? 30
Right.
to 1.
30 to 1 is immobilization.
Throwing numbers out.
She's just throwing numbers, hoping and praying she gets them right.
I'm like picking numbers.
She's
off the
okay
paper.
though. Like eventually she'll be right. And
Here
so
it is. It's this top corner.
so-
Immobilization.
immobilization. But if it's less than what number, do we get a net mineralization?
20.
Less than 20 to 1. So would blood meal result in a mineralization or immobilization?
It's less than 20, so it'd be mineralization.
Mineralization. What about fruit pulp?
That would be immobilization.
Immobilization. What about biogenic waste?
It's in the middle ground.
Yeah, right. And then what about the yard waste?
Immobilization.
Immobilization. So just to kind of understand that your carbon, and we saw this when we did the math, right? The higher the carbon nitrogen ratio of the residue, the more immobilization happened.
Right.
Because there's so much carbon that the microbes can't, they need 8 to 1
Yeah.
in order to break the rest of that carbon down.
Okay.
And if it's not enough, then they have to find it from the soil. So they will take that out of the soil. That's why we need to know how much we're, the immobilization potential, then we can offset that with fertilizer.
Okay.
All right? That is it. Thank y'all so much for showing up.
Sorry, I didn't know where to go.
That's all right. I didn't leave a note on the door. That's my fault.
We're gonna be up here from.
I don't think we're going to have class next Friday.